going to be looking at the geometric series. Before we look at the geometric series, let's first explore what a series is and what it means for the series to converge or diverge. So some basic terminologies. A sequence is a list of terms that are arranged in a particular order. 1, 4, 7, 10, 13, ... This means this sequence continues on forever. It's an infinite sequence. We can name a sequence in this fashion, a sub n, usually in the curly brackets like that. Sometimes you'll see it with the brackets, sometimes not. Okay, but usually it's supposed to be in the brackets right here. N is called the index. It tells you the terms placed in the sequence. So A1 would be the first term, A2 would be the second, and so forth and so on. A sub n is considered the general term, the term that is the form that all the other terms follow. So you'll see that coming up here. The AP exam often uses K for this index instead of N, so be prepared. N, K, M, it doesn't matter the letter they use for the index. Just know that the purpose of it is to tell you its place and to represent the sequence as a whole. Okay? The nth term, like I just said, the nth term of expression is a formula that will allow you to find any term in a sequence. We learned this back in the early days. This was the explicit formula. For the sequence I just showed you up here, 1, 4, 7, 10, 13, what is the pattern we notice? Well, that's where we do the common difference and things like that. You see that we're just adding 3 each time. If I add the same number each time, then that's going to be times 3 each time, so it'll be 3 times n, and then to get the rest of the numbers that you need is minus 2. So the first term of the sequence, if I plug in 1 in here, I'm going to get 1. If I plug in the second, so this for the second term, so if I plug in 2 in here, a sub 2 is the second term. If I plug in 2, I should get the number 4, and I do. 6 minus 2 is indeed 4. 13 is the fifth term. So if I plug in 5 in here for the fifth term, 3 times 5 is 15 minus 2 is 13. So it is a rule that allows me to find any term in the sequence. Sum of the terms of a sequence is called a series. So if you add up all of these terms, that's called a series. Okay? Because it goes on forever, this is called an infinite series. Well, what if I don't want to add them all up? What if I only want to add up the first 10? Well, if I only add up a certain number of terms, then that sum, which was usually denoted as a capital S, gets a little index number on it indicating how many terms you're going to add up. So that's what this means. This is now a partial sum. I'm only going to add up the terms up to whatever this index number here is. Okay? So let's take a look at, in a geometric sense, what this looks like. Okay? So, if S1, okay, is 1/2, so if I take a 1 and cut it in half, then the sum of only the first term would be this. And then if I cut that in half, then I have this plus this. This is 1/2. This is half of that, which is 1/4. 1/2 plus 1/4 is 3/4. So now I have 3/4 of the whole thing. What's this third sum? The third sum is 1/2 plus the 1/4, and cut that in half, it gives me 1/8. Add those up, it gives me 7/8. And we can just keep on going here. Cut that in half, gives me a 1/16 here. And keep adding it all up. Now I have 5/16. And if this pattern continues infinitely, so I keep cutting in half and adding and cutting in half and half and half and half and half, and I do that forever, what does this sum equal? Or does it equal anything? It equals 1 because this this infinite series will consume the entire area of the 1 by 1 squared. So what this tells me then, since it's confined in here and it will eventually reach the value of 1 if I go to infinity, okay, then I have what was that sum converged to a number. Okay? If the sequence of partial sums has a limit, so let's look at that again. What am I talking about? The first sum was 1/2. The second sum was 3/4, then 7/8, then 15/16. That is the sequence of the sums. Okay? If that sequence of the partial sums If that has a limit L, then the infinite series converges to that limit. And this is what you write. So here is the sum of a sequence. If I take the limit of that, as n goes to infinity, then that will equal the limit of the partial sums of that sequence, and that's equal to L. If the sequence has partial sums diverges, then the infinite series also diverges. So if those partial sums did not settle in on a number, did not equal a limit, then the sequence itself does not equal a limit either, and it also diverges. When an infinite series converges, we often call that sum S. Okay? If this thing converges, it will converge to a number, and that sum, that limit, is called the S, the sum of the sequence. So a little heads up here, there is only one sequence you're really going to be asked to find the sum on, and that is the geometric series. Okay? The only series you're going to ask to find a sum on is usually the geometric series. The other ones are just too difficult to find. All they really want to know is does it converge or diverge. But this one we're going to delve in a little bit more deeply for the actual sums. So let's go ahead and look at some examples and see what we have going on. Start with the first one here. I'm given this sequence, the one we just looked at. Write an expression for the nth term, and then find the limit as that goes to infinity. Okay, so we already kind of looked at this one. What's going on here? Well, if I have a fraction, if I want to find a rule for something like this, and it's not going to be arithmetic, or we look to see, can it be geometric? If I can't add the same thing each time, which I can't, we already know that from the previous look at the geometric sense of it, can I multiply the same thing each time? And now you can see, yes, I can. I'm multiplying by 1/2. 1/4 times 1/2 is 1/4. 1/4 times 1/2 is 1/8, and so forth and so on. And so because of that, I can find a sub n is going to be 1 over 2 to a power, and that power is going to be whatever term I'm in. So I'm in the first term here, so I have to get a 1 here. I'm in the second term here, so I have to get a 4 here. So it just has to be whatever the term number you're on. So the general term of this sequence, a sub n, is 1 over 2 to the n. What is the limit of that as n goes to infinity? Does it have a limit? Well, if this number here is going to infinity, then the bottom number is getting larger and larger and larger, but the top here is not. So 1 keeps getting divided by a larger and larger and larger and larger number, meaning this entire fraction gets smaller and smaller and smaller and heading towards 0. So the thing to look out for is this a geometric sequence? A geometric sequence? Yes, because I am multiplying by the same quantity each time. It's geometric. So the sum is going to have there's going to be a sum for things. And so we can check this out and see what it is, and you can kind of do the partial sums here. There's 1/2, and then we already did this. This is what we did on the other side. 1/2 plus 1/4, 3/4, and then s of 3, and so forth and so on. This one we found to be 7/8. And then s of 4, on the previous notes we found this to be 15 over 16. And then the sum of n is 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus ... 1 over 2 to the n. So that is what a partial sum up to n is. Okay? You can put that in a table and kind of see what's going on. But if you remember, okay, so if we look at this, then what is s sub n? Put these numbers into it. Excuse me, I went ahead of myself here. I got to put my table in. So take this sequence of these sums and let's put it into a table. This is how we did it back in the early days. So in the first sum I have 1/2. In the second sum I have 3/4. In the third sum I have 7/8. In the fourth sum I have 15 over 16. Okay, so what do I have in the nth sum. What pattern do I notice here? Or is there a pattern that I can notice? So what is the sum in a different format from this? What would I get if I added all these up? Remember, these are just fractions and all that kind of stuff, so you would basically do common denominators, change all the fractions, and add all the numerators. Okay? We can also look at this and see if there's a pattern. Since I have a fraction, think of this as a fraction. What's the bottom pattern? 2, 4, 8, 16. Well, that just looks like a timesing by 2. So this is just simply going to be 2 to the n. Now let's look at the top. The top, look at the relationship. This is the number I'm plugging in. It is almost that number, correct? But it's not, this one it is, but what's happening here is I notice that this top number is just one less than the bottom number, isn't it? So if the bottom number is this, then the top part of the fraction is that minus 1. And that gives me that little pattern right there. I can then take this and rewrite it by simplifying it as 1 minus 1 over 2 to the n. And then I take the limit as n goes to infinity, okay, of that quantity, one minus 1 over 2 to the n, and we already established that that right there is going to be 0, so this just simply becomes 1. And that tells me then that the sum of the series is equal to 1. Okay, so let's look at some of these other things down here. Before I do that, let's look at some other information, excuse me. So this is what I had written right here. We just did this example here. Let's look at the geometric series. So that we don't have to recreate that all the time. A geometric series is the sum of the terms of a geometric sequence. In a geometric sequence, you have an initial number, and then you're multiplying by a common ratio each time. The geometric sequence follows in an exponential function form. So a sub n, the nth term, the generic term, is an initial number times r to a power of n. And then we know from back in our time we did this that the common ratio is greater than or equal to 1. The sequence is going to diverge, and if it is between 0 and 1, the sequence will converge. Well, if the sequence converges, then what's the sum going to be? Well, the sum is going to be this formula right here. Okay? Where this a is the first term of your sequence. Okay? And so r is the common ratio. So this is the one in the formula you get to use, okay, to help you find the sum of a geometric series. This formula right here. And we are going to use it. This is the one you need to have memorized. Okay? So part of what you're going to be asked to do is, can I recognize a geometric series when I see one? And then can I find all the parts that I need to find the sum? State whether each of the following series are geometric. If yes, then identify R. So how do I do that? Okay? So what you're looking for is you're looking for a pattern. And the best way to look at it is maybe write out the first couple of terms and see what you have. Now, the geometric pattern is you want R, okay, to be between 0 and 1. Any repeated term R is going to be geometric. But for it to have converge, then you want to make sure that R is like less than 1. So what's going on here? I have 1/2 raised to a power. So that means I'm multiplying 1/2 each and every time. Is it of the form something to a power? Can I get this to look like that? And the answer is yes. Okay? In this scenario right here, R is the 1/2. Does this look like that? R is a common ratio. That means it's a number. This is not a number. That's always the same. This one number changes. This was supposed to be the exponent, so this one is no. It's not geometric. But what about this one? Is this one geometric? Well, at first glance, the answer is no, it doesn't look like it. But let's look at this in a little bit more detail. Okay? The negative exponent makes this look like a fraction. Okay? But that doesn't matter so much. But our exponent rule, our rule over here is this is positive. So a negative exponent means that e to the negative n is the same thing as 1 over e to the n. Now, that is a number. And I'm raising it to a power n. So yes, this one is. And r is 1 over e. Okay? So there's that one. Let's take a look at another example that I have. This time we're going to be evaluating some geometric series and state whether the series diverges. Okay? So here's right here, this is a number to a power, which means r is 1.1. And because that is greater than or equal to 1, what do I know from this? Because it's bigger than 1, this will diverge. That's what I know. Okay? What about this one? Well, if you can write it in a certain format, it makes it easier to see. And that format, once again, is what? For geometric series, I'm looking for this form. Can I get that form right there? So I want to have an r and I want to have a power of n. Well, I can separate this out. And I'll just do it with the number part so you can see it. Actually, I'll do it this way. No, I'll do it this way. So this is 3 times 1 over 2 to the n, which I can then write as 3 times 1 over 2 to the n. 1 to the n is just 1. So there I have that format. So r is equal to 1/2. It is geometric. Okay? And not only that, but because this is less than 1, then I know it will converge. And so I can find the sum. The sum is going to be a over 1 minus r. So I know r, but I need to know what a is. A is the first term of this series. So what is the first term? So plug in 1. If I plug in 1 into this, I'm going to get 3 over 2. If I plug in 2, I'm going to get 3 over 2 squared. I need that number to be on top. 3 over 2, 1 minus 1/2. So if I work that out, I can give you the series. Okay? So here's a little thing I want you to look at. I have some side notes and stuff I want you to use. Take a pause here, write those down so you can have them. So this sum right here is this. For r, it's interpreted a little differently here. N does not begin at 0. We need to think of a as the first term of the series. So even though if you look at this as the formula started at 0 and ours did not, it didn't matter. A is the first term. Okay, the first term of that series. So think of it that way. All right, let's look at some other examples I have down here. What about this one? Well, yeah, it's already in that form. So r is 3 over 2. But does it converge? Well, no, this is bigger than 1. So this here will diverge. All right, now here's a weird looking one. All right, let's take a look at this. Let's play along with some of these things. So I know that E is approximately 2.718. I know that pi is approximately 3.141. So what is R? What is a negative E pi? Well, if I take this value as an absolute value, so ignore the negative portion of it, it's going to be between 0 and 1. Take a look at it. That number divided by that number is less than 1. A negative, absolute value is ignores the negative. So this number is between 0 and 1, which means this series will converge. And if it converges, then I can find the sum. The sum is the first number in this sequence, so let's take a look at it. Here we have n is 0, So if I plug in 0, anything to the 0 power is 1. Then I plug in 1, I'll get this thing. But I don't care about the next term. I'm just showing you what it does. So my first term is 1. So 1 over 1 minus r, which is a negative e over pi. And then I can work this out through the magic of mathematics, and I can get an exact answer that looks like this. Why don't you try practicing the manipulations of this to get to that? Okay? And then you can always give a decimal approximation. Just remember, if it is decimal, it's an approximation, not an equals. Okay? So that is the geometric series, and we will continue on with other convergence problems in later videos.